Storage Engine Specific Optimizations Part 2 of 2. Now this particular exam objective, friends, to me is a bit of a fudge. And what I mean by that is this. By looking at optimizing merge and memory storage engines, the MySQL team really wants us to understand how to use the merge and memory storage engines. In my experience as a MySQL developer and MySQL DBA, I've found in practice that not too many DBAs use storage engines beyond the two that we've already discussed, MyISAM and InnoDB. And I'm not exactly sure why that is. Maybe it's the old habits die hard. Maybe it's just that most MySQL DBAs are busy men and women. I'm not sure. But at any rate, in this nugget, we're going to take a look at how the merge and memory engines work and what best business cases factor into their implementation. Let's get working. The merge storage engine. Of course, the question of the day is, what is the merge storage engine and why would we use it in business? The first answer that I have for you, friends, is that the merge storage engine is a logical collection of MyISAM tables, and these MyISAM tables have identical structure. And you're thinking, okay, Tim, tell me more. That doesn't really tell me much. What do you mean, a logical collection of MyISAM tables? Well, again, I'm going to string you along just a little bit. I'm playing with you a little bit here, kind of building anticipation. Before I give you the benefits, let's dive right into the code and let me show you how the code works, and then I'll give you the benefits. In the code here, which I've pulled from the MySQL reference manual, you see that we're building two tables, T1 and T2. And you'll note that both of these example tables are very simple, and that simplicity here is by design, so we could just look at the general flow. We have a column named A that is an integer. We're constraining to not null. We're using auto increment, and we're setting the primary key constraint. No big deal. That's just a perfectly fine column. Second column uses message with a char 20, and we're setting MyISAM as the engine. Now, both of those tables, you'll notice, have the exact same structure, the very exact same column names, exact same data types, and the exact same properties and constraints. You also see in the middle part of this sample code, we've run some inserts on those two tables. Now, the values here are almost identical. In the upcoming demo, I'm going to put completely different data in these two tables. But in the sample code on the MySQL reference guide, for whatever reason, those folks put in almost identical data except with the third row. They did T1 for table T1 and T2 for table T2 for the third insert. Now we finished the code out by creating a third table called total. And I'll jump right to the bottom here after our column declarations. You notice that for this third table, we're switching up our storage engine to merge. Now then, to come back a step, you'll notice still we're using the same two column names, the same two data types, but you notice a couple differences. We're not attaching the primary key constraint to the column A. Column B, we're adding an index to column A, but we're not adding primary key. Now, you should know by now that when you do add a primary key constraint on a column, an index is automatically created on that column. The deal is with the merge storage engine, you actually cannot create a primary key constraint. So if you want to build an index on that column, the way to do that is to actually build an index on that column manually, and that's what you see going on here. Finally, after the engine declaration where we assign merge as that engine, we use the union keyword to combine rows from both of those tables, in this case T1 and T2, and then we have an optional property called insert method, and this takes one of two keywords, first or last. Now you're following along, I'm sure, because the code I've described is pretty darn straightforward. You're in essence creating, well, you're not in essence, you're actually creating a table called total that is combining the rows from table 1 and table 2. And so the upshot of this is that we can direct our users at the total table, and those selects will union or aggregate rows from T1 and or T2, depending upon which rows the user is retrieving, you see? Now that could potentially bring back a tremendous number of rows. The insert method is important if and only if your merge table is going to involve inserts. If you plan on inserting data, in this case, you're going to have a T1 table and a T2 table. Here's the question, because your merge table is really a logical table that's not going to store rows in it directly. There's the question, do inserts need to go over here in T1 or over here on T2? If you do insert method last, then any inserts will be put on the right side of your union declaration, in this case on T2. If you do insert method first, then inserts will go on the left side of your union declaration, in this case the end of T1. Simple as that. In some ways, the merge storage engine functions like views do in terms of being a logical entity that aggregates data from two or more tables. However, a merge table has some stricter elements that you don't get when you're using views. Now that you understand the basic mechanics behind the merge storage engine, let's take a look at some of the business reasons why we might want to implement merge. We'll also discuss some of the file system ramifications of implementing the merge storage engine in MySQL Server. Merge optimization benefits. Actually, before we talk about these benefits, let's back up and talk about the file system implications of setting up a merge table. Now, you know by now that with MyISOM, you wind up with at least one data file. Whoops, let me get that extension correct. An MYD data file, and depending upon how many indexes you build, one or more MYI indexes. Now, when you create your merge file, or your merge table, I should say, MySQL Server will create two files on disk in that database directory. You wind up with your traditional format file for the table. Of course, you'd also over here for any other MyISOM table have a .frm format file. To recall, the format file defines the structure or the schema of the table. However, the merge file also gives you a .mrg file. You don't get an MYD file that stores rows, remember. A merge file gives you a .mrg file. The contents of the merge file are the names of the tables that should be used as one or as a logical entity. Now that we've covered that architectural detail, let's discuss these optimization benefits. The biggest one, and I'm going to throw an asterisk here because this is the really big exam alert that you'll probably see on your tests, is that the merge storage engine allows you to overcome OS file size limitations for MyISOM tables. Depending upon your operating system on which MySQL Server is running, and depending upon the file system that the OS is sitting on, you may be dealing with a cap as to the maximum size that .myd file can grow. Now, in the previous nugget where we talked about row pointers, remember I mentioned that as of MySQL 5, we have those 6-byte row pointers, and we can grow our MYD file, our table file, to just well over 200 terabytes theoretically. However, like I said, you may have an operating system or file system limitation that's going to prevent the file from growing that large. One way, or the chief way that MySQL team suggests you get around this, is to break out your table into multiple files and then build a merge table that brings together those separate MYD files. You see what I'm saying? Now it starts to come together for you, I hope. That's the biggest plus to using merge. You can get around some of the problems. Now, of course, there's the question, how are you going to get these separate MYD files taken care of? Well, there you'd have to do some extra work. You'd have to create what are called symbolic links or symlinks to tell MySQL where those separate MYD files are. Now, that process is beyond the scope of the exam objective, so we don't have to worry about it. I would recommend, if you're interested in doing this in production, that is to say, if you're interested in moving your table MYD files to separate physical hard disks or separate partitions, you consult the MySQL reference manual. You know, it's our best friend, as you know, and you'll get the full skinny on creating those symbolic links in your data directory. But that's the biggest advantage of merge. Another advantage of using merge is that you can save disk space. Now, we talked in the previous nugget about compressing MyISOM tables. You see how easy it is to use MyISOM pack to do that. You can actually build a merge table that blends both compressed and uncompressed tables. Remember, the compressed tables are read-only and therefore good only for archival data. You'll want to be careful if you're supporting inserts to make sure that you do not direct inserts toward a compressed table, or you're going to generate errors for obvious reasons. Finally, we have the important advantage of merge tables supporting more efficient table maintenance. And there it's pretty simple. Because we have our core MYD data broken out into separate data files, we can perform table maintenance, table optimization, index rebuilds, etc. on separate MYD files while keeping the rest of the data online. So users can continue to hit the merge table, and as long as those queries are not hitting the MYD file that's under construction, as it were, or is under routine maintenance, those queries would continue to run unperturbed. Isn't that great? The second and final type of storage engine we're discussing in this nugget is the memory storage engine. Now, what would we use the memory storage engine for? Well, the memory storage engine is a really fast storage engine that's used for temporary data storage. So your knee-jerk thought might be, well, this is more of a developer-oriented storage engine, isn't it? And yes, it's true. The memory storage engine is particularly suited to MySQL development. The memory storage engine will store all data except the .frm format file in the server RAM. Therefore, as I've said several times now actually, your data access is going to be exponentially faster than from pulling that raw data from disk. However, the hazard is you want to be careful not to load too many rows into your memory table because of the fact you're chomping on RAM content. And depending upon how often your server is restarted, that table could continue to persist in RAM indefinitely. You see what I'm saying? Now, the bottom line is when you create a table using the memory storage engine and reboot the server, although it purges the contents of the memory table, if you look in your data directory, you'll still find in the appropriate database a table format file, a .frm, that gives you the structure of the table. If you run show tables for that particular database, the memory table name will still be there. It's just that it will be devoid of content. If you run a select splat, you'll get nothing back. And as you'll see in the upcoming demo, you can always manually run a truncate table command to clear all of the data and yet keep the table there. Of course, you can drop the table if you actually want to nuke it and delete it fully from disk. What you're seeing in the main portion of the whiteboard is a helpful summary table of all of the features conveyed by the memory storage engine. As usual, I pulled this content from the appropriate article in the MySQL reference manual. You don't need to memorize this for the MySQL DBA2 exam, of course. Just know some of the major highlights, namely that the memory storage engine, believe it or not, does support indexes. So you can create a table and actually index the content. So you're starting with table data that's fast out of the gate. Imagine how faster yet it is building indexes. However, you cannot do full text. We know about full text indexing now. Locking granularity, table, well, that should come as no surprise if you're aware of the fact that only InnoDB supports row-level locking. Let me see. Anything else? Compressed data, no. Well, that's significant. That tells us that we cannot compress an in-memory table. Again, no surprise. We know that compressed data is archival and is meant to persist over time. You can replicate memory tables. That's quite interesting also. No foreign keys. That's just an architectural fact of life with MyISOM. And then finally, transactions, no. So there's really no surprises here. Most of what you see on this table are simple hallmarks of the MyISOM engine and are simply shared or carried over to the memory storage engine. No big surprises. Really, the biggest thing for you to remember is that the memory storage engine is volatile and the fact that you can create indexes on it. The two specific optimization tips regarding the memory storage engine that I have for you is that you can set a system variable called max heap table size to cap the amount of RAM consumption by memory tables. It's nice that the MySQL development team gives us this. Otherwise, you could very well wind up with runaway memory-based tables, especially if not everybody on your team is up to speed with the ins and outs of MySQL storage engines. So be aware of that. The other optimization tip is to consider flushing your memory tables periodically, again, just to conserve server RAM. And as I've already said, the two ways to do this, the least invasive, of course, is to run truncate table, which simply removes all of the row data from the table, but keeps the table standing, as it were. If you don't need the table anymore, you can run drop table. That's actually going to remove it not only from MySQL Server, but delete the file from the file system. Now it's time for our fun demo. In this demo, we're going to play around with both merge and memory tables. Now, if you've looked at my DBA1 CBT Nugget product, I cover not only the merge and memory storage engines, not only the MyISOM and InnoDB storage engines, but also all of the additional storage engines, all of the remaining storage engines that ship with MySQL Community Server. However, if you do own that product, I want to make sure that I don't duplicate too much. We'll keep things fresh and interesting for you. Let's put on our MySQL DBA hats and have some fun. All right, we're going to perform this demo on WinNugget 1, our Windows Server 2008 box. I've opened an elevated command prompt and logged into MySQL Server. We'll start by creating a database called DB1, just a shell. We'll then use DB1 and start our work. First part of the demo we'll work with is the merge storage engine. Now remember, to set things up, the merge storage engine requires that we have two or more MyISOM tables with identical structures. Therefore, we're going to create a table called T1, a simple table. First column, we'll use the integer data type. We'll specify not null. We'll have it automatically increment, so we don't need to worry about it incrementing its value. And we'll also assign the primary key constraint to it. Col2 we'll set to char20. And then even though I'm reasonably certain, positive actually, that the default storage engine on this server is MyISOM, after all, this is a fairly freshly installed server, I'm going to specify the engine declaration of MyISOM just for grins. Cool. Now there are different ways we can create a table from an existing table declaration. However, I'm going to create T2 from scratch just so you can see the full code and have some time to admire it. Okay, so once we submit this second batch to the MySQL parser, we'll have T1 and T2, two identically structured tables. Now we can show tables. There they are. And to verify that they're the same, we can show create table T1, show create table T2. I understand this is overkill. We just want to be absolutely positive that those tables have the exact same schema. Having done that, let's run maybe a 3 or 4 row insert on each one of those tables. We'll insert into T1. I'm just going to insert into col2. Because we've assigned the auto increment property to col1, we don't have to worry. We can just let that increase. And in table 1, I'm going to put in some random food objects here, all of which begin with A. How's that? So we'll put in apple, artichoke, and apricot. Actually, I put col1 instead of col2, so let me correct that. There we go. Now let's do the same thing. I'm going to save myself some typing by using the up arrow, just editing some of our text. Now we'll do an insert into T2, and this time I'm going to put in some food items that start with B. How about banana? How about bread? How about bacon? Everybody's favorite food. Cool. So no big surprise so far. The inserts and the selects are working all day long. T1 and T2 are separate tables. Now, of course, the real-world situation is we've got those files getting bigger and bigger and bigger, and maybe behind the scenes we've now moved those MYD files to separate file systems, and now we're going to create a merge table to gather them together into a single logical object that we can query from. So let's do this by creating a single merge table called T3, or actually let's just call it TBL merge. We'll give it a descriptive name. We have to use the same column names, same data types. So let me scroll up here, remind myself what I did. I've got col1 int not null, auto increment, col2 char 20. And why don't we slap an index on col1 just to give us a speed advantage. We'll close up our column declaration, and then here's where the money is. We specify engine is merge. We need to union out our participating MyISOM tables in whatever order you see fit. It makes sense to just go T1, T2 here. And then if we're going to support inserts, we're going to do insert underscore method equals first or last. I'm going to do last here. So that's all there is to it. So we'll run show tables, and now we have table merge added to the list. Let's run a select splat from TBL merge, and we see, just as expected, first our T1 values, our A's, then our T2s. And of course, we could run select star from TBL merge, where col2 is like A, to generate just the A's, and so on. You know, selects are selects, no big surprises there. To really start pushing the envelope, let's try an insert on this. Now to come back up to our DDL statement, remember that we specified our union order of T1 first and then T2 second, and we specified insert method equals last. Therefore, if we now say or type insert into TBL merge, and we're going to insert not col1. Remember, col1 is going to be an automatically incrementing integer. We don't want to mess with that. So we're just going to insert a col2 value, values, and then let's insert, how about something that's neither A nor B? How about something like mango? What's going to happen? Well, we get an error, don't we? And you know why. Let me up arrow again, and correct. This is real world stuff, no question about it. Press enter, get a new line, fix my error, go ahead, submit to the parser, query OK, no warnings. Remember, we could invoke show warnings if we did have a warning, just to tie in something from an earlier nugget. And the query was okay, so therefore let's run some selects. First, TBL merge, and we see 1, 2, 3, apple, artichoke, apricot, 1, 2, 3, banana, bread, bacon, and we see 4, mango. Of course, the question of the day is, we know that table merge itself is a logical entity. Where is the actual row stored? Well, let's do a select star from T1. We just have the 3 rows. Let's run a select star from T2. And because we have insert method equals last, we have mango showing up as row 4 in T2. No big surprise. Let me open up the data directory just to finish this part of the demonstration off. And in datadir, we have our DB1 folder. This was our database we just created. And we have our format file, our MYD, our MYIs for our first 2 tables. And then for our merge table, we have our format file and our .mrg file as previously discussed. Just wanted to show that to you. Great. All right, so onward and upward to the second and final part of this demo, and that is working with memory tables. There's really nothing to this. This is going to be a very quick exercise. We just simply say create table. In this case, why don't we make this one T3? And I'll just make this col1 int not null auto increment primary key col2 char 20, just like it was before. And we'll just say engine equals memory. Show tables, show table status, like T3. Probably want to do that with a backslash uppercase G, and it tells us in the engine field we're using the memory storage engine. I probably shouldn't have closed my datadir window. If I come back to DB1, I now see a T3 format file as promised, and this is going to persist across server restarts. But as I add data to the T3 table, it will be loaded into memory unless and until I execute a drop table, or if I just do truncate table T3, that will clear the rows of the table. That's all there is to it, friends. Storage Engine Specific Optimizations Part 2 of 2 Review. In this nugget, we took a long, hard look at two not so well known, but very useful in specific circumstances, storage engines in MySQL Server. First, we saw Merge, which is very highly attached and is in point of fact dependent upon the MyISAM storage engine. We saw that as long as we have two or more MyISAM tables with identical, underline that, identical structures, we can combine them into a single logical merge table that allows us to overcome OS file system problems. Very good to know that storage engine. The second storage engine we looked at is the memory storage engine, which gives us super fast, temporary data storage in MySQL Server. I hope that this has been informative for you, and I'd like to thank you for viewing.